Hello everyone, my name is Alex Palivani, and today I'm going to talk about PostgreSQL 17 and its top new features. Those features will have something for everyone who is working with PostgreSQL, either they maintain large, highly scaling systems or are trying to create new applications. Those features are including such things as incremental backups, the thing which will basically let you spend less on your backup copies, both storage and processes. We're also going to talk about improvements in support of SQL JSON, a new function which will let you work with JSON formatted data the way as if it was the relational data stored in a table. And in the end of this presentation, we are also going to briefly cover some performance improvements in different areas of PostgreSQL, including vacuum, query improvements, B-tree index improvements, and asynchronous I/O. Stay with me while we are going through these sections. So let's talk about incremental backups. What this feature basically is, what benefits it gives to its users, and how it was implemented in PostgreSQL 17. What is basically an incremental backup? We are talking about the case when we created a full copy of our database at some moment of time, and then we want to capture and store only the changes in the dataset. So we save space, storage space, and also decrease the time needed to complete a single backup operation. Benefits which incremental backups give their users include reduced storage requirements, you need less space to store less data, faster backup times, so you don't need so much time to complete just a small portional backup, simplified database operations, which means that when you need to restore or clone your existing database, you can do it faster and with less number of steps, and saving costs for cloud or your on-premises storage. So the less space you need to store some number of backup copies, the less it's gonna cost you in the end. Now let's talk about how incremental backup works in PostgreSQL. The existing tool, PG-based backup, was enhanced with new capabilities to support incremental backups. So now you can add a specific flag, which is I, which stands for incremental. With this option, you can refer to an existing full backup copy. And this will let you create incremental backups, for example, for different full backup copies if you, for some reason, prefer to have many of them. Now you should use full backup as a baseline, which means that initially, yes, you have to create at least one full backup copy. So it's gonna take time, but only once at the beginning. And then this full backup is going to serve as a starting point for all subsequent incremental backups. And what else was added is a manifest file, the file which describes the changes between the prior full or incremental backup and the current backup event, thus allowing PG-based backup to track which data blocks have changed since that point in time, which is quite important, and we're going to stop on this in a moment. Now let's look at the three basic steps which comprise this incremental backup strategy. So you have a full backup where you use PG-based backup without the I option, without this flag to create your first full backup copy. Then you use the same utility but with a new flag specifying the full backup location with its manifest file to create an incremental backup. And all the subsequent incrementals, all the new incremental backups in future should specify the same manifest file of the most recent previous backup. So every time you basically refer to what we've done the last time. Now let's start from this point in time and just capture all the changes and save them as a new incremental backup copy. Let's move to the practical examples. So here you can see how we create a temporary folder to store our backup files. Then we enable wall summarizer, and I want to go over this part in detail. So a new process was added to PostgreSQL, responsible for finding and tracking those changes in data in order not to write all changes for the same row, because we don't need to store changes for a row which has been changed 10 times since the last backup. We just want to take its final state, right? So to remove all the interim states this record has gone through. So here we enable this process by altering the running instance. Then we create the database just for the sake of example. We create a table there and we fill it with some temporary data, 10,000 records. After that, we create a full backup as our starting point. So we run pg-based backup, we provide the output directory where we are going to store our backup copy, and we list it on the screen just to give you the view of what it looks like. In this folder, as you can see, we have the full copy of our configuration files and data files, along with a new file called backup manifest, which we discussed earlier. So this is a manifest which describes this backup copy and specifies that, for example, this is a full backup. Now we are going to go back to the database and add more data to the table to simulate the changes which usually happen in the real world. So we are going to add another 10,000 records to the same table. Then we are going to create an incremental backup specifying the full backups manifest file with this new flag called I. As you can see, the new directory is very similar to what we've seen in the full backup folder, but it also smaller in size, and its backup manifest is a bit different. And I'm gonna show you that in a couple of minutes. So we are checking the backup label file. Here you can see the label tag. And you see that we are using base backup here in our incremental. So this is a sort of a reference. And we see that this backup is incremental by the last two lines on the screen. So it's incremental from the specific logical sequence number, the position in our transaction log, or talking in terms of PostgreSQL wall. And if we go further, the way how you can restore this incremental backup is just providing it all the backup directories in the proper order. So you start with the full backup directory, which is followed by incremental backup folders in the order of their creation, from the earliest one to the latest one. The last parameter on the screen is a new output directory where you are going to restore the database with configuration files and data files and run the new database cluster from that directory if required. To conclude this section, I'm going to talk about comparison between incremental backups and so-called point-in-time recovery. In the current PostgreSQL version, you can first take a full backup copy and then just write down or archive each wall file with all transaction changes happening since that point. This will let you restore the backup, then replay every change which has happened since taking this backup copy up to a specific point in time which you are interested in, thus recreating the data directory as it was at that point. So you basically say, I want to see my database on this moment in time, and you can achieve it. So usually this technique is called point-in-time recovery. Logically, the result of a point-in-time recovery up to an incremental backup point, so the moment in time when you created an incremental backup copy, should be the same as restoring this incremental backup at that point. So you just go to the same point in time in two different ways, but the destination is the same. The difference, however, is the size of the incremental backups. So if we just sum them up, you will see that often their size is less than the combined archived WAL file size, because you simply don't need to store all those interim changes. If this approach meets your requirements, and you are fine to have less storage used by your backup copies and faster time of recovery provided by this new strategy, then you can basically go with it. But if for some reason your system requires the ability to be restored to a specific moment in time, no matter if it's the day when you created this incremental backup or 5 seconds later, then you should go for a point-in-time recovery strategy. Now let's talk about PostgreSQL JSON improvements. PostgreSQL 17 expands the existing features related to work with JSON data. We are going to talk about JSON table, which is a function which basically converts JSON data into a relational table format, thus simplifying your work with it within a SQL environment. So you can query it, or you can, for example, use it in your DML statements. And the benefits of this new improvement include flexibility in working with various data formats under the umbrella of the same database engine. So if you want to use only PostgreSQL to work with data, here you go. So what is JSON? And this is a good question for us who are used to this format for more than a decade. As per Wikipedia, JSON or JavaScript object notation is an open standard file format and data interchange format that uses human readable text to store and transmit data objects consisting of name-value pairs and arrays, which is quite a boring definition. If we look at the example on the bottom of the page, this is what JSON documents look like. So you see that those curly braces are used to define an object with two attributes. Their names is on the left of the column and their value is on the right. So here we have two attributes. The one of them is a simple string and the other one is an array. Now, what PostgreSQL added in this version is JSON table function, the function which is going to make your life so easier if you work with JSON in the database. This function allows you to query JSON data and present it as a relational data set, which can be accessed as a regular SQL table or view. You can use it inside the from clause of a select, update, or delete, and as a data source in a merge statement. For those of you who for some reason missed that, yes, we have merge in PostgreSQL. Taking JSON data as an input, JSON table uses a JSON path expression to extract a part of the provided data to use as a row pattern for the constructed view. And we are going to see it in a couple of moments in a more practical example. Each SQL JSON value given by the row pattern serves as a source for a separate row in the constructed view. From a developer's perspective, JSON table significantly simplifies working with semi-structured formats, and we will show you why. So this is a syntax tree. It may look a bit overwhelming, but there is nothing complicated actually happening here. So we have the context item where we are going to take our JSON formatted data from. We have a path expression, like which part of this JSON formatted data we are going to parse and use. And we have this passing syntax. This is the value, and we can actually have multiple values here. We have columns. Each of them represents a relational table column, which we are going to get as a result. And also what to do when, for some reason, we face some error in the data. So for some reason, the data is invalid. For JSON table column, as you can see, we have quite a broad variety of options. So we have pass expressions. We can decide to keep or omit quotes on string values, which we can get from this JSON. We can decide what to do with nesting if we want to. So we want to take some part of the JSON, which is nested in the JSON, which is nested in the JSON. And now we are going to jump to the more interesting part, which are examples. Okay, so here is our first example, which covers passing for ordinality, path, and exists clauses. As you can see on the screen, we have the query, which queries JSON formatted data and tries to display it as relational data. In our document, we have a single attribute with an array of 2 records, apple and banana. And we pass in a value as a variable, which is used on the line below. This variable is called a price limit, and we want to show all the variables where our price limit is greater than 15. We also have row num for ordinality. This way we add in a sort of a calculated column. So for each new record, we increase this number by 1, and you can see it as the first column in the result. Pass clause is used to specify that we want to show price as our column, and item as our column called item name. This way we can rename attributes if for some reason we do not like their current attribute name. And we also can use exists, which is used in the last line of the column part. So this is our filter with this variable. Let's move to the next example. The next example is about nesting. So we actually have JSON data inside the JSON data, and we want to dive into this document and extract this data from the depth. So here we have the nested paths, as you can see on the line, starting with this clause. And we specify that we want to get items as a separate table, because we have the document where orders is an array of independent separate JSON objects, and we need to get to them with this nested path expression. And here is the result of this query. As you can see, we can bind order ID to the specific item from this order on the same screen, the same way as if we worked with relational data into tables. The third example shows you how to query JSON from a table. So here we store our JSON formatted data in a table, which is created with the first statement. We add in 2 different rows there, the row with a user named blue and the row with a user named unblue. We are not too original. And then we are trying to select this data from the column with JSON values in this query. So as you can see, we can pass the name of the column, which is the first parameter to JSON table called JSON data. We also provide the JSON path. So we want to look for a user attribute, and we specify 2 different columns for those users, username and user age. To summarize what we've just seen for JSON table, as you can see, for a developer whose daily work is connected with processing, querying, updating, and displaying JSON data, this new feature brings more value and gives more flexibility. Now let's talk about performance enhancements in PostgreSQL 17. We are going to cover such things as new memory management system for vacuum. It reduces memory consumption and improves overall vacuum performance. We will see optimizations of common table expressions and union queries. We will take a look at improving B-tree index performance, where handling of in clauses or filters with multiple values was optimized to provide faster query execution for operations involving large datasets. And we are going to touch on streaming I/O changes, which led to faster data scans during such operations as analyze, PG preform, and sequential scans. And we will talk about their benefits for PostgreSQL users overall. New memory management system for vacuum. Who knows what vacuum is? For those of you who don't, vacuum is a maintenance operation which reclaims storage space occupied by dead tuples. That means that in PostgreSQL, multiple versions of data are created to let concurrent users work with the same data without locking each other. But it is achieved at a price of creating multiple versions of data. So let's say I update the record and you update the same record. Now we have three different versions of the same data. One is the original version of this record, and we have one version per both of us who have updated this record. So something or someone needs to clean up all this mess, and in the end of the day, leave only a single version of the record with all the changes committed. And this process, this mechanism in PostgreSQL is called vacuum. So to remove those tuples, those versions of records from a table, it also takes PostgreSQL to update an index if the table is indexed, because an index basically stores references or pointers to data records in the table. How PostgreSQL does it? It actually starts a process called auto-vacuum, which goes to the index, removes the stale index entries which are obsolete, so that to be able to actually fully remove the dead tuple from the table. And the process has to track references to dead tuples while doing all this work. Starting from the version 17, a new internal memory structure is introduced for vacuum, which incredibly reduces the memory consumption. This new data structure is called TED-store, and it has replaced the previous array-based approach, which resulted in huge reduction in memory usage, up to 20 times less during vacuum operations. It also eliminated the previously available limit on memory usage. So we used to have this 1 GB memory usage limit for vacuum tables. And if you need to clean up huge tables, like with massive changes happening over time on them, then 1 GB is not enough. So you need more. You need to clean up a terabyte of data. It may be not enough for you to store all those references while changes keep happening on this table. So, and you cannot simply say to your users, hold on, give me 3 days to complete my vacuuming. And it also improved overall vacuum performance. Less data to look up, quicker operations to perform. The next topic is optimization of common table expression queries. In PostgreSQL, and not only in PostgreSQL, but in many other database systems, a common table expression is a temporary named result that you can define within the scope of a single query and reuse multiple times. So, for example, you want to store a specific set of filters, like values, and you want to reuse it in a huge query for, let's say, 10 times. You can define such set of rows at the beginning of your query, give it some name, let's call it my filter, and then use it as a regular table. CTEs help you to keep your code more readable, modular, and it actually eases its maintenance in future. Most of the database systems use with keyword to define them. PostgreSQL 17 has introduced several significant improvements to materialized common table expressions, such as changes in how optimizer or planner lets CTEs to propagate column statistics to the outer query. So in other databases, you may know it as a predicate unnesting. Now, what does it mean basically? Basically, if you use a table with available statistics and planner can see that in your common table expression you refer to this table, then it can unnest or inline the content of this common table expression in places of the query where you refer to it. Thus, using statistics from the inside of this common table expression and coming up with a better plan, which results in a faster execution. And the second part of that is that now we have passkey propagation. What does it mean? It means that now the planner can know the order of rows in a result set. So it may help you to get a faster query by eliminating the need to sort the same result twice, since you know it's already sorted within the CTE. So you can skip this part during the execution and just use the data. Now, the optimization of union operators. The union operator in SQL is used to combine the results of two or more select queries into a single result set. And by default, it eliminates duplicate rows from the result unless you specify the all keyword. PostgreSQL 17 brings significant enhancements to the union operator. Now Optimizer uses merge append access path to merge sorted input streams. So you have two different row sets, and now PostgreSQL understands that it can go through both of them simultaneously, switching between them once the sorting key has changed. So instead of doing this work sequentially, it can parallelize this work and even reuse indexes on the same table to properly process different segments. Now, improved B-tree index performance. PostgreSQL 17 introduces better handling of multi-value searches in B-tree indexes, particularly for in-clause lookups. What does it mean for us? Let's imagine a query where you want to receive the list of employees for departments with the department code 1, 2, 3, or 4. And you simply list those values in your predicate. Previously, PostgreSQL would perform searches for each value in the in-clause, which means that it would go and look for all employees from the department 1, and then it would go and look for all the employees from the department 2, and then for the department 3, and so on, which in a case of a really long list of values would result in a significant execution time. Now, during a single scan, PostgreSQL can consider multiple values, which for our example means that instead of going and checking each record if it actually passes the filter for the department 1 and then for the department 2 and then for the department 3 and so on, we will do it in a single lookup. So we will just check a record against all the values at the same time, which means that for a case with 4 different filter values, we just did 4 times less job. Imagine what the benefit could be if we work with tens and sometimes hundreds of values in this list, which is used in a filter predicate. So this improvement should result in a huge performance gain for systems which let their users to specify multiple filters. So let's talk about Streaming IO API. But before we start, we need to clarify what a buffer or a page is in PostgreSQL. Buffer or a page is a fundamental unit of data. So this is basically pieces each table is made of. When performing operations like a sequential scan, PostgreSQL reads many buffers at once. PostgreSQL 17 introduces a new internal API for streaming reads, allowing the database to read multiple blocks at a time, rather than one at a time. This is a key step towards asynchronous I/O, or so-called AIO. The new API also allows for more systematic use of calls like POSIX-F advanced will need for random page access, which helps the operating system load needed pages ahead of a time, basically predicting what your query is going to need in future. Larger or so-called factored IOs can replace many smaller IO calls, reducing the overall overhead for the system. So why is this important? Even without full asynchronous, I/O streaming reads can improve performance due to reduced overhead and more efficient interaction with the operating system. And the group of developers which have been introducing asynchronous I/O all over the place in PostgreSQL started with gradual changes, thus letting us see how the system improves over time with new versions when we replace synchronous I/O with asynchronous one in specific calls. The next benefit is about sequential scans, which now can perform larger reads. Instead of reading data by the size of the buffer, or 8 kilobytes by default, we can talk about at least 16 times larger chunks of data. Analyze operations are faster due to smarter prefetching. Yes, if you read more data at once, you can calculate what data is stored in the table and come up with its statistics faster. So this sounds reasonable. This API refactoring is also a crucial step for implementing full asynchronous I/O in future versions of PostgreSQL. And the setting which was added, which is called the I/O combine limit, can be used to adjust the size of I/O calls, which can be beneficial for different file systems. So if you run your PostgreSQL database on something exotic, now you can adjust the way it reads from the underlying file system with your setting. I'd like to say thank you for joining today's presentation, and we are going to keep you updated on any new feature which new PostgreSQL versions are going to introduce in future.